Hello everyone, this is Akshay here, and welcome to my channel of the GFG Pewd streak of day 128. And if you're new to this channel, please like, share, and subscribe so that we can learn, grow, and maintain our streak together, right? So today I'm not switching on my video here because um, the camera is having some malfunction here. So let us resume without this live feed. I'll try to fix it as soon as possible, and then from the tomorrow, I hope I'll be able to switch it on. Okay, so let us read the question and see what are the different approaches we can code in, we can think of. So let's read the question first. So the question name is the number of good components. So given an undirected graph with v vertices, numbered 1 to v and e edges, find the number of good components in the graphs. Okay, so we have to find the number of good components. So what exactly is a good component is? A component of the graph is good only if the component is a fully connected component. Okay, so what is exactly fully connected component then? It is a subgraph of given graph such that there is an edge between every pair of the vertices in a component. Thus that there is an edge between every pair of the vertices. Okay, so if one vertex have an edge to the second one, then it must have the edge to all the available vertices, right? And simultaneously for all the vertex. Okay, we will see. Then the graph can be a disconnected. Okay, the given graph can be a disconnected graph. Okay, so if it is a disconnected graph, then we have to run. We have to iterate for each and every possibility, right? For each and every node. So that requires a for loop. So consider the adjacency list from index 1. Okay, I've considered it. Right. So 1, 2, and 3 is given, and the explanation is given as that we can see there is only one component in the graph, right? And in this component, there is an edge between any two vertices. If I see at 1, then it has edge between 3 to 2. If I see from the point of 2, then it has between edge to 1 to 3. Similarly, for 3, it has edge from 1 to 1 and 2. ठीक है यार. But for this graph, the output is 2, and the explanation is that 1, 2, and 7, there is no edge between 1 and 7, correct? Okay, so each and every vertex is not having an edge to rest of the remaining vertex. That is why 1, 2, and 7 is not our answer. And for the rest of the thing, 3, 4, 5 is are connected to each and every pair, each and every vertex connected to each and every remaining vertices. So that is fully connected. And 6 has no other vertices, then it is also counting as like a single standing node is also counted as fully connected component. Okay, so we have understood the question, I guess. So what we can do here, can we derive any relation between the vertex and the number of edges so that when we iterate, or first of all, yeah, what we have to do in this question is the graph. It's a graph question, so it can be solved using simple DFS recursive traversal. But while recursively traversing it, we have to maintain a base case, right? We have to finalize a state where we will reaching our answer. So can we derive any relationship between the number of vertices and the number of edges if it is a fully corrected graph? So let's talk about the let's talk about the three node system. So if it's a three node, then the fully connected graph has three edges. So let's assume that there are four nodes now, right? So each and every vertex must have the edges to all the remaining vertices. So if I see at point of this node, then it has the edges to this node. Let's say A, B, C, and D. So A has the vertices to B and C, but not to D, right? So let's draw it. Similarly, B has edges to A to D, but not to C. So let's draw it. So now I guess each and every vertex has edges to all the remaining vertices. So if the node is 3, then I can count the number of edges is 1, 2, 3, 4, and this diagonal 1, 2, so 6. So for 4 it is coming as 6. Can we derive any relationship here? So for 3, what can I do? 3 into, let's do n plus 1, so it will be 3 into 4, so it will give us 12, right? But we have to reduce it, so let's do by 2. So 12 by 2 will be 6, so 12 by 3 will be 4. Okay, so let's start with this direction. So 3 into n minus 1, right? 3 into 2, so it will be 6, but if you divide by 2 it will give us 3. Okay, let us use this formula for the second one as well. So 4 into n minus 1, that is 3 by 2. So, okay, so that's the formula then. So if for a fully connected graph, if we just know that how many vertices are there, and how many edges are there, then by using this formula, that edges should be equals to b into b minus 1 by 2, then in that case I can say that particular component is my answer. So I will do answer plus plus for that, right? So I just have to write a recursive code of this graph, and then we can we can code the thing. Okay, yaar. So how we can do this? How we can do this is, it was written that it was a disconnected graph, right? So I have to start from one, because it has also said that the vertices are starting from one, and I should be less than equals to v and I plus plus, right? For each and every vertices, I have to make a DFS call, right? DFS call, let's say pass the adjacency list and the starting pointer, right? And for each and every call, I have to let's say v count. I have to maintain a v count and an edge count, right? Then only I can do the comparison at last here. I will do the comparison here, right? That if edge count is, if it is equals to what, v into v minus 1 by 2, right? V count into v count minus 1 by 2, right? So initially it will all be 0, right? So while writing our recursive code, what we have to maintain, what we have to do is that first of all we have to maintain a visited array, right? Because if we have visited, let's say we started from 1, if we have visited 2, right, then I don't want to visit it again, right? And from 2 I will make a recipe equal to 7, then I don't want to repeat this 7 again, right? So what I will do is, first is that I will make a global, I will make these two variables as global, as well as this visited array also, because I have to use these two things as well as a visited array in my recursive, right? So okay, so I will make one int v count, and I will make one int e count, and I will make one visited array, right? And I will just say, while traversing the DFS, what's the standard thing, that you have to mark this point as true. So I will say that it is true, and then I will, whenever I visit a vertex, I will say count plus plus, and then I will increment my edge count, and edge count is nothing but, what is the edge count? So for this thing, for this graph 1, 2, and 3, for this graph 1, 2, and 3, the adjacency list will look like that: 1 has the neighboring elements as 2 and 3, 2 has the neighboring elements as 1 and 3, and 3 has the neighboring elements as 1 and 2. So if I just consider this size, this for a particular index, if I consider the size of the array list, then I can say then these are the edges that will be in the part. So for 3 I can see there are two edges, one to 1, it is going to 1, and another to 2, and that is nothing but the count of the array list each index is having in the 2D array list, right? So I will say edge count is nothing but plus equals to, I will use this adj, and I will say that get of st, right? And uska size nikalo yaar, get the size, right? And for that thing, and for rest of the children, for let's say neighbor, in what, adj dot get of st, I will call the DFS again, right? If it is not visited, then only I will call the DFS again. If not visited of what, neighbor, then call the DFS of pass the ADJ again, but at this step I will pass the neighbor node, right? So I hope this is very clear. The pseudocode is very clear to you. In the standard DFS code, we mark it as visited. We count the number of nodes as per our requirement is here. We count the number of edges, and then for the next of the neighbors, we iterate, right? So let us see. Let me give you a quick dry run of this graph, right? So for this graph, when we have as 1, 2, and 3, what will happen is I will call the DFS for 1, and I will say that v count is 0. And now since I have visited this thing, then I will say v count is 1, and edge count is nothing but the size of the array list it is having. So 1, 2, and 3, it is 3, 2, 1, and it is 2, 1, and 3. So what is the size of the list the one index have, right? It is 2. So I will say edge is updated from 0 plus 2, that is 2, right? Now next what I will do, I will call for its next of its neighbors. So let us, the neighbor are 2 and 3, which is not visited, and I will have this boolean array 0, 1, 2, 3 as visited. So as of now only 1 is visited, and since I have called the DFS for 2, I have to mark it again as visited, and I will say now v count, since that was a global scope, I will do 1 plus 1. I have visited a new vertex, and I will use the edges again. So it will be 2 plus the array list which have 2 is, the size is 2, right? 1 and 3, it has the 2 edges coming from 2, this one and this one, right? So I will do 2 plus 2, that it will be 4, right? So are there any neighbors of 2 that are not visited? Neighbors of 2 are 3 and 1, but 1 is already visited, so I will call DFS for the remaining one, that is 3, right? And I will do vertex plus 1, the three nodes are now have been visited, that it is a part of a same recursive call. One, the 1, 2, and 3. These are part of the same recursive call. And edges is nothing but, again, 3 has the two edges coming out from 3. So it will be the previous edge 4 plus 2, that is 6, right? Now the 3 has no more neighbors which are not visited, right? So it will stop here. It will go back to the parent call. It will go back to the parent call, and the recursive function for I equals to 1 will stop here, right? And I have to check now, since 1, 2, and 3 were visited in one recursive call, that means they were definitely connected. But we do not, but that they, but to ensure that we know that it is connected, right? Because we call from 1 to 3, DFS 1 2 3, right? But to ensure that this is fully connected, we need to check the relationship between the number of edges and vertices count we have, right? So edges is now 4 plus 2 is 6, right? So that means that we have counted the edges twice, right? So for 2 I counted this and this edge. For 3 I counted this edge again, right? Since this is an undirected graph, so that means I'm counting a same edge twice. So what I will do is I had to check that v was into v minus 1 by 2, right? So now since edge is already in twice in number, so I will do multiplication by 2 here, and it will cancel out. So now the condition is changing, that e should be for this for a particular code here, the behavior should satisfy that the e should be equals to v into v minus 1. So is it satisfying that 6 is equals to 3 into 3 minus 1, that is 2? So it is satisfying, right? So I will do answer plus plus. And for I equals to 2, it will not run because 2 is already visited in this array, right? Similarly, for I equals to 3, it will not run because 3 is already visited in the array, right? Similar dry run will be solved for this case, 1, 2, and 7. First, the DFS will call for 1. It will see that how many edges are there, right? Then 2, it will call for 7, right? Right. So try to dry run this second test case for yourself, and if you are like good to go, then try coding it. So pause this video here now. Take help of the pseudocode. Try the dry run for the next test case. Give yourself a 10 minutes time and come back to this video again, right? Okay. So I hope you were able to do at least this some part of the coding thing. So ठीक है. So this question requires, I think we are just 11 minutes now in my video. So let us do the live coding here, right? So ठीक है. So the first step was to make some global variables, right? So let's make it. So it will be static int. Okay, so I have declared the variables here, right? So let us initialize our visited array. That will be nothing but new boolean of number of vertices plus 1, because the vertices are starting from 1 base indexing, right? Now what you have to do, that I have to call DFS for all vertices, and I have to maintain the vertices count and edge count for each DFS call, right? And for each DFS call, let's make a DFS call for each and every vertices. So it will be I equals to 1, I less than v, I plus plus, right? And for each call I have to check that first if it is not visited, right? So I will check that if it is not visited, this I, then call the DFS, right? So I will call DFS of ADJ and the starting node, that is I, right? And also for each and every vertex, I have to initialize my v count. The v count is equals to 0, as well as edge count to also 0, right? So v count equals to edge count equals to 0. Yes. So let's implement the DFS function now. So I will say, since this will be a void function, so I will say that int void DFS. Now I will pass this array list ADJ, and int starting point, right? Int start, right? So for the first standard point will be that mark that point as true, so that we do not recur back for the same node, right? Since we have visited the starting point, do count plus plus and increment the edge count also, and edge count will be nothing but coming from the adjacency list. So access that index node. So my node was starting, right? So access that 2D array list using the start point and get its size, right? Get its neighbor, because the number of neighbors will the each number of edges coming from this vertex will be the number of neighbors it have, right? Okay, now the last step will be that iterate for neighbors, not iterate, recursive call for its neighbor, right? Then only we will say that these components, the number of nodes, the recursive call having for each node will say that these number of nodes will is connected in is are connected, right? Similarly, I do your DFS of 1 call to its neighbor DFS of 2, DFS of 2 call to its unvisited neighbor, that is DFS of 3, right? So this ensures that 1, 2, 3 are definitely connected. But to ensure that it is fully connected, we need to apply this logic as well, right? So let's get back to the code. So for int neighbor, let's access the to-do list for adg.get of st, right? I have accessed the neighbor now. So if that neighbor is not visited, right? Since this visited was a global scope array, so it will be accessed by the recursive call by a function anywhere, by each and every function, let's say. So DFS of I will call it adj of, now starting point will be its neighbor, right? Okay, so here after this if I will have the components, I will have that which are all the vertices are connected, and I will have the vertices count as well as the edge count, right? I just need to check that that if e count, the if edges count is equals to what? V count, right? Star of like multiplication of v count minus 1, right? If it is equals to itna this v into v minus 1, then what we have to do? We have to do answer plus plus, and for this thing I have to make one variable as well, that is int answer is equals to 0, and at last I will do nothing but to return the answer. So I will say return my answer. That's it. So let's compile and run, and then we'll see for ourselves. Okay, so there are some typing mistake, I guess. So there is something expected at the end. Okay, so there is one parenthesis expected because you have not closed the if statement. Let's compile and run again. Okay, so there is some output and our output has to mismatch. Let me look at the code more carefully. Okay, so the mistake is like for each and every DFS call I made, right? So when the DFS call is over, in that at that particular instance only I have to check the condition, right? So this if which I have written outside my this previous if statement where the node was not visited and making a call, in the same if I have to check this condition as well, right? So that was maybe a typing mistake. So our logic was definitely correct. So expected output and output matches, and that was the intuition. So I hope you were able to relate to this logic and the code. And let's just talk about the time complexity before submitting the button. So what will be the time complexity? So what I am doing is for each and every vertex, I am calling DFS for its adjacent neighbors, right? So every vertex will have the neighbors as the number of edges it have, right? So it will be the time complexity will be v plus e, right? Because it will look like that for every vertex I am doing e times the edges time traversal, right? But it is not it's not the multiplication, because whenever I am visiting the edge, for suppose for one there were two numbers 2 and 3, right? So when I DFS call for 2, I mark it as true. So when I'll be coming at 3, I will see that its first edge, that is 2, it is already visited, so I will not visit it again, right? So that is why it is not v star e, instead it is v plus e, that is all the number of nodes and edges associated with it. So it will be v plus e time complexity, and since v and e both are equals to 10 power 4, so v plus e will be nothing but 2 into 10 power 4, which is definitely less than 10 power 8, and if our logic is right, which is, then it should definitely get submitted, right? And the space complexity will be that visualize the code again, visualize the diagram again. For 1 I called it for 2, for 2 I called it for 3, right? So let's say 3 again, it has a branch with 4, and the 5 is here as the disconnected component, so 3 will call for 4 again, right? So that means the time complexity will be the node with maximum uh, connection, right? or we can also say the depth of graph, the depth of graph, right? That how long a particular node is connected. This, in this case, 1, 2, 3, and 4, right? So it will be O of 4. If there was another node, let's say 6, which was connected to 7, 7 again connected to 8, 8 connected to 9, and 10, and so on, then that would be like, this is the longest particular subset of graph, then that would be the the node which has the maximum connection, that is 6 here, right? So I hope you are relating to this point as well. Space count is nothing but the number of recursive calls you are storing in your recursive stack. So this will definitely get submit, and let's hit the submit button now. So we are already 20 minutes and counting. So let's end this video as soon as possible. Okay. So the code got successfully submitted, and let me give you a quick code walkthrough. That we made some global variables, then we ran a for loop for each and every vertices. If we check that if it is not visited, call the DFS. For each and every DFS, we maintain a vertex count and an edge count, and we verified that a graph to be fully connected, the edges count should be equals to v into v minus 1 by 2. We have not done by 2 here because when we were counting the edges, it was calculating uh, each and every edge as one more redundant, right? So if the edge was coming 3, it was calculating at 6, right? So that's why we didn't do the division here, right? So that is how it is going. And this is the DFS function marking the node as true, maintaining the edge count and the vertex count, and recurring for its neighbor again, right? So that was the logic that we so here's the logic also, that we do not this multiplication 2, right? Because edges was coming already itself as 2, right? Okay. Okay, so that's it. And for the initiative I've taken, that for the C++ users, I will give you the C++ code as well. So it should not, the language should not be a barrier for any learner. So this is the C++ code, and here is the Java code that I already explained you, right? So that is it for today's video. Let's meet again in the next POTD streak of day 129. And okay, a few last thing, that you can start and fork my DSL repository, as well as you can connect me on Instagram and LinkedIn for any doubts and guidance you have. Use the comment section constructively to ask doubts. I will definitely try to solve your doubts in each and every manner. And till then, bye bye, take care, keep learning, keep growing, and bye.